Good morning, students. Today I shall discuss the topic rotational spectroscopy. Rotational spectroscopy is also called as microwave spectroscopy. So first question arises, why it is called microwave spectroscopy? Rotational spectroscopy are observed in the microwave, that is far IR region, with wavelength of order 100 micron or more. This spectra results entirely due to the changes in the rotational energy levels of the molecule. So what happens? There are so many energy levels, or you can say there are different types of energies in a molecule, such that rotational energy, vibrational energy, and electronic energy. So these type of energies are obtained in different regions of radiations or electromagnetic radiation. So we know that there are these type of radiations. First is radio wave. Radio wave, first one is, then it is microwave, then it is infrared, then it is visible, then it is UV, ultraviolet, X-ray, gamma ray, cosmic ray. So these are the electromagnetic radiations which we know. Here from left hand side to right hand side, energy and frequency. Energy and frequency increases, and from left hand side to right hand side, wavelength, that is lambda, decreases. So on the left hand side, the waves are of higher wavelengths, and as soon as we move from left hand side to right hand side, the wavelength decreases, but energy increases and frequency also increases, because from formula we know that E is equal to h nu, or E is proportional to nu, h is the Planck constant. So when energy increases, frequency also increases. So here this rotational spectroscopy is from this microwave region. This region, when used, that is when microwave is used, it only brings changes in the rotational energy levels, because there are so many energy levels. If these are the electronic energy levels, if these are the energy levels, then there are some vibrational energy levels. These are electronic energy levels. These are electronic energy levels. These are vibrational energy levels. Vibrational. These are vibrational energy levels. And between these energy levels, there are rotational energy levels. So rotational energy levels are denoted by J, vibrational energy levels are denoted by V. So today we are discussing microwave spectroscopy or rotational spectroscopy, because when we use microwave radiation, only changes take place in the rotational energy level, that is from this type of energy level, not from this energy level, because these are vibrational energy levels. These are vibrational energy levels, and the small splittings are the rotational energy levels. Now, our first question is that why rotational spectroscopy is called microwave spectroscopy. This is because here we use the radiation from the microwave region, and hence it is called as microwave spectroscopy. Now, another question is, what do you mean by rigid rotator model? When there are no changes in the bond length of a diatomic molecule, suppose this is a diatomic molecule, these are the two atoms which are bonded together, and this is the bond between these two atoms, and if there is no change in the bond length of a diatomic molecule, then it is called as a rigid rotator. And if during rotation this bond length changes, then it will be not called as a rigid rotator, it will be called as non-rigid rotator. So therefore, in the rotational spectroscopy, our first assumption is that the bond length between the two atoms of a molecule is not changing, and hence it is called as rotational rigid rotator. Now, next question arises, why it is necessary to use quantum mechanics to explain the rotational spectral lines? Because we know that before quantum mechanics, the mechanics which we were using was classical mechanics, and classical mechanics predicts the absorption of radiation at all wavelengths, and it will result in continuous band. Continuous band means there will be no discrete energy levels. It will have a continuous spectrum, or when all the energy levels come close together such that they cannot be separated, then that is called as continuous band. But in the rotational spectra, we find discrete energy levels. When we take the spectrum, in case of rotational spectroscopy or microwave spectroscopy, we find fine discrete lines, and therefore in order to define these discrete lines, quantum mechanics principles are used. Now, first of all, we calculate the moment of inertia, which is denoted by I, capital I, of the molecule when we are dealing with the expression of rotational spectroscopy or microwave spectroscopy. So here I have represented the diatomic molecule. A and B are the two atoms. M1 and M2 are their masses. The distance between the nuclei, center of the nuclei of these two atoms is small r, and this point is the center of gravity. From center of gravity to the center of the nuclei, distance is r1, and also r2 is the distance between the center of gravity and the center of the nuclei of the atom B. Now, these are here parameters are written. M1 is the mass of atom A, M2 is the mass of atom B, R is the phase distance between A and B, that is called bond, and R1 is the distance between center of gravity and the center of mass of M1. Similarly, R2 is the distance between center of gravity and the center of mass M2. Now, moment of inertia of any system consisting of n particles consisting of I particles can be given by I is equal to M1 R1 square plus M2 R2 square, plus dot dot, or if there are I particles, then mi into ri square. Or in short, we can write summation I mi ri square, where r1, r2 are the distance of respective particles from center of gravity to the center of masses. In the present case, we will have we have two particles, because we are dealing with diatomic molecules, and the model is called rigid rotator. So for two particles, there are two terms in the in this expression. I is equal to m1 r square plus m2 r2 square plus m1. So when we are using only two terms, I is equal to m1 r1 square plus m2 r2 square, equation number 1. Now the system is balanced about its center of gravity, therefore this condition is valid. That is, m1 r1 is equal to m2 r2, means mass, the product of mass and the r is the distance between the center of gravity to the center of the mass of that atom. Similarly, m2 is the mass of the second atom, and r2 is the distance between center of gravity of that atom to center of gravity to the center of mass of that atom 2. Now from figure we know it is very clear that r is equal to r1 plus r2. This figure is, this r is equal to r1 plus r2. So here we have written equation 3. Now from equation 2 we again write m1 r1 is equal to m2 r2, and here we put the value of r2, and r2 means r minus r1. So when we solve this equation for r1, we get the value like this, m2 by m1 plus m2 into r. Similarly, if we calculate for the value r2, it becomes r2 is equal to m1 by m1 plus m2 into r. Now putting these two values, m1 r1 and r2 in equation 2, this is equation 1. So here this is equation 1. I is equal to m1 r1 square plus m2 r2 square, and in this equation if we put the value of r1 and r2, then expression becomes like this. And when we solve this equation, then finally we get the expression m1 m2 by m1 plus m2 into r square, and this expression, this term in the expression is nothing but it is reduced mass denoted by mu. So here we have put I is equal to mu into r square, and equation 4 is there. Now expression for energy of rotational energy levels. Since the rotational energy levels are quantized, the molecules have only certain definite value of rotational energy. The quantized energy levels of rotational spectra are obtained by applying wave mechanics and solving the Schrodinger wave equation with concept that molecule is rigid, that is potential energy is 0. So this is very important concept, that when we use the concept that molecule is rigid, that is this is a rigid rotator molecule, in that case the potential energy, that is V, will be equal to 0. This is the Schrodinger wave equation in 3 dimensions, and in this case here we will put V is equal to 0 because molecule is rigid rotator. And from and for these 3 terms we use del square psi. This is the operator system notation. So del square psi plus 8 pi square m by h square E into B into psi, and if we put B is equal to 0 because potential energy is 0, so equation reduces to del square psi plus 8 pi square m by h square E is 0, so E into psi is equal to 0. On solving, this equation, we get the solution for E, and the expression becomes E is equal to h square by 8 pi square I into j plus 1 R's, where j is the rotational quantum number. Here we have not written, but j is the rotational quantum number and h is the Planck constant, I is the moment of inertia we have derived in the previous page. Now, the energy of rotating molecule, which have been calculated as equation 5, can also be obtained in another way, because we know that I is equal to E is equal to E is equal to half I into omega square. This is similar to E is equal to half mv square. This equation is very similar to the equation kinetic energy. E energy is equal to half mv square, but in this case here mass is replaced by the moment of inertia and velocity is replaced by the angular velocity. Therefore, the equation becomes E is equal to I half into I omega square. And if we multiply and divide this expression with I, then it becomes I square omega square by I, and I into omega is called angular momentum, denoted by L. So L is the angular momentum and L is equal to I into omega. So if I into omega is replaced by L, then it becomes L square by I, and according to quantum mechanics, the angular momentum is given by the expression L is equal to h by 2 pi under root j into j plus 1, where j is the rotational quantum number, h is the Planck constant. So for this L, if we put the value here, then h by 2 pi under root j into j plus 1 whole square divided by I. On solving, we get this type of equation. This becomes a square, h square by 4 pi square I, and this root vanishes and becomes j into j plus 1. On multiplying, h square by 8 pi square I, j into j plus 1 arcs per mole. Equation 5, j is the rotational energy levels, h is the Planck constant. Here it is the unit, how it has been obtained. So if this h square by 8 pi square is written in terms of rotational constant, then rotational constant is denoted by B, and it has value h by 8 pi square IC, where c is the velocity of light. So if we want to write the equation 5 in terms of the rotational constant, then it becomes E is equal to B h c j into j plus 1. Now, in case of rotational spectroscopy, the spectrum is represented in terms of the wave number in the units per centimeter inverse. So the energy should be converted into the wave number, and if we divide the energy by h into c, then it becomes wave number, because mu bar is equal to 1 by 1 by lambda, and E by hc, E is equal to h mu. So if you divide E by hc here, this is equal to nu by c, and nu by c is equal to 1 by lambda, because c is equal to nu lambda. So 1 by lambda is equal to nu by c. So it is equal to nu bar, and that calculation has been written here. Nu bar is 1 by lambda, and if we divide energy with hc, then it becomes 1 by lambda, that is nu bar. There is a question that show that rotational energy levels are not equidistant. Here we have drawn some rotational energy levels denoted by J. So the first one, lowest energy level is J is equal to 0. So first one is J is equal to 1. Second one is J is equal to 2. Third is equal to J is equal to 3. Fourth one is equal to J is equal to 4. And just now we have derived the expression for nu bar. Nu bar is equal to Bj into J plus 1 per centimeter. So if we put J is equal to 0, then nu bar becomes 0. If we put J is equal to 1, then it becomes 2B. If we put J is equal to 2, then it becomes 6B, then it is 12B, and it is 20. Now here we see that the distance between first energy level, rotational energy level, and second rotational energy level is 2B, but the distance between the second rotational energy level and third rotational energy is 4B. Similarly, if we see the distance between the third rotational energy level and fourth energy rotational level, then it becomes 6B. Here the difference is 6B. Similarly, for fourth and fifth rotational energy, distance is 8B. Now it is very clear that here the distance is 2B, 4B, 6B, 8B, that is not distance. So the question is that rotational energy levels are not distance. This is due to what? This is due to the value of wave number of different rotational energy. Now, what do you understand by the selection rule? This is a very important term in the spectroscopy, in the all types of the spectroscopy, because the transitions which take place from one energy level to the another level, either in case of rotational energy level or in case of vibrational energy level. Here the rule which is applied is the selection rule. So what is selection rule? Selection rule in short we can say that it is a condition by which any transition can take place, and that is governed by quantum mechanical principles. So here some terms are required to explain the selection rule. So here selection rule defines the transition probability from one eigenstate to the another. Actually it is the probability of transition from one energy level to the other energy level, and transition probability is defined as the probability of a particular spectroscopic transition to take place. Now selection rules are utilized to determine whether a transition is allowed or not. If it is if transition takes place, then it is called allowed, and if transition does not take place according to certain rule, then it will be called as forbidden transition. Selection rules are derived on the basis of quantum mechanics by the help of transition moment. So some mathematics is also required here. When an atom or molecule interact with a suitable electromagnetic radiation, it can induce a oscillating electric or magnetic moment if the frequency of the induced electric or magnetic moment is same as the energy difference between one eigenstate psi1 and the another eigenstate psi2. The interaction between an atom and the molecule, or a molecule and the electromagnetic field, come in a state of resonance. The amplitude of this electric or magnetic moment is called transition moment. Actually, a resonance takes place, and resonance takes place only when the energy of the electromagnetic radiation and the energy of atom in the particular state becomes equal. So if quantum mechanics in quantum mechanics, the transition probability of one molecule from one eigenstate psi1 to the another eigenstate psi2 is given by m21. It is a vector square where m21 is called transition dipole moment or simply transition moment from psi1 to psi2. Mathematically, this type of expression can be written m21, which is dipole moment or simply transition moment, transition dipole moment or transition moment. So this is equal to integration psi2 mu, which is a dipole moment operator, and psi1 d tau. D tau is the small volume element, and delta x into delta y into delta z. N is the number of molecules in this system. Qn is the charge on each molecule. Xn is the position vector operator. Now this selection rule describes how the probability of transition from one level to the another cannot be zero. The selection rule describes how the probability of transition from one level to another cannot be zero. If it becomes zero, then transition will not take place. So it should not, its value should not be zero to occur at transition, and if transition occurs, then it is called allowed transition. Otherwise, it will be called as the forbidden transition. Now, from next lecture, we will start from the selection rule of the rotational transition, because every transition is governed by the selection rule.